In this module, we are going to talk about EIGRP summarization and filtering. When it comes to EIGRP route summarization and route filtering, we have to separate these two a little bit. And I'm first going to talk about the summarization process, the IP route summarization. And EIGRP supports, generally speaking, two forms of route summarization. It supports automatic summarization, which depending on the iOS version may actually be turned on by default, or it may be turned off by default, or it may be completely unavailable to you. Automatic summarization is, let me state this out of the way, is better turned off. What it actually does is, when the routes are advertised to the neighbors, EIGRP process is going to look and attempt to summarize these routes at their classful boundaries, where classes are obviously Class A, Class B, and Class C. Since let's say 1993 or 1994, we are using CIDR, or the classless interdomain routing, and variable length subnet masks. This feature is not necessarily that useful. It is easily turned on with auto summary under the EIGRP process, and it's even more easily turned off with no auto summary. If you happen to be using iOS 15 or newer, auto summarization is turned off. If you are using iOS with the version number lower than 15, auto summarization will be turned on. And you should, as I said, turn it off. A much more useful feature is the manual summarization of routes. Manual summarization is called manual because you have to explicitly configure what routes you want to summarize with what prefix. This is easily done, and depending on how you configured your EIGRP, are you using the traditional way of configuring it, that's what I like to call the numbered mode, or you are using the new named mode of configuration, this summarization will be configured in two different places. If you are using the numbered mode, the summarization will be configured under the interface, and the syntax is very simple. IP summary address, EIGRP, AS number, and the prefix that you want to summarize. In a case that you are using new mode, that you are using the named mode for configuring EIGRP, the summarization will need to be configured under the EIGRP process, under the address family, and there under the AF interface configuration for the interface that you want to summarize on. And in all of these cases, EIGRP is automatically going to install a route that is called the discard route for the summary with a default metric, with the default, administrative distance of 5, pointing to null zero interface for the summary that you just created. The purpose of this route, so-called discard route, is the loop prevention. And I'm going to talk about this in a little bit more detail. But you know what? Talking about a summarization without actually seeing it in action doesn't make much sense. So let's take a look at a practical example of IP route summarization in EIGRP. The network that I have pre-configured right now consists of just two routers, my R1 and R2, and they're interconnected on gigabit interface 1 on both sides, and the network between them is 10.0.0/24. And what I have here is .1 and .2, and between them I have EIGRP in AS12 configured. On R1 I have configured this using the traditional numbered mode, and on my R2 I have configured this EIGRP process using the new named configuration. And what I have also done on these routers here, I have a large number of, I shouldn't say a large number, but I have a certain number of static routes pointing to a fictitious gateway there, and I have redistributed these routes into EIGRP, and from both sides these will be from 192.168.0.0/16 range. So all the routes that we are going to be seeing in this EIGRP exchange between R1 and R2 will be from this range. But as we will see, there's going to be a large number of these subnets. So we are going to look at how we can summarize them, where we can summarize them, and then we are going to explore some of the options. And we are definitely going to look into how discard route loop prevention works. I'm going to start this example by looking at R2 first. So what I'm going to do is I'm going to do show IP route EIGRP, and I'm going to take a look at what are the EIGRP routes that I might have. And I can see that I have really significant number of these routes, but let's pick one of them. So what I'm going to do now is I'm going to focus on these subnets, on these two subnets here of 192.168.64.0/24 network. Now, if I take a look at this output here, at this routing table output here, I'm going to see that this doesn't really make much sense. If I take a look at, for example, this, it's going to say that 192.168.64.0/25 is subnetted and that I have two subnets. But what is the mask on these two subnets? Well, this is a problem with iOS. The problem that it has been written and designed and implemented very, very long time ago, and it still suffers a little bit from this classful behavior. So what iOS is actually telling me here is that I have 192.168.0 network that uses the fixed subnets of /25, and that I have two subnets from this major network. If you ask me in 2013, 2014, 2015, whenever you are actually watching this video, this is rather silly behavior. What it should tell me is that I have 192.168.64.0/25 and 192.168.64.128/25, but unfortunately it does not. Now, I can use some of the other commands. For example, I can do show IP route 192.168.0 255.255.255.0 longer prefixes, and actually let me see, what did I make mistake here? So it's not 0, it's 64. So what I can do here is I can run this command, but it's still not going to give me the output that I want. But what I need to look at here is, for example, 192.168.64.0/25. If I look at this particular subnet explicitly, that means that I already suspect this might be the mask, then I'm going to see that, yeah, this is the actual routing entry that I have, 192.168.64.0/25. And I'm going to see the same thing for 128. So this is unfortunate thing dealing with iOS, but once you get a little bit of a little hang of this, and when you develop a little eye for figuring out these subnets, this is going to be second nature, and you're not even going to notice that iOS exhibits this weird and unusual classful behavior. But let's go back to our summarization. So I have these two subnets of 64/24. Let's summarize this from R1 when we are advertising these routes to R2. Let's summarize them as a single /24. I can do that. Before I do that though, I would like you to take a look at one thing. These two routes are received on R2 as external routes, and we can see this here. It says these are EIGRP external routes. So I want you just to remember this for now. I'm going to go now to R1, and what I'm going to do on R1, before I start doing anything, I'm going to say show IP route EIGRP, and these are the routes that R1 received from R2. We can see here that these routes are all subnets of 192.168.100 network. I just want you to remember that as well. So here we are dealing with 64, and here we are dealing with 100 network. Now, the interface interconnecting R1 and R2 on R1 side is gigabit interface 1, and on this interface is where I need to configure my summarization, because remember, R1 is configured using the traditional numbered mode, so this is exactly where I need to configure my summarization. So I'm going to go to interface gigabit 1, and I'm going to say IP summary address EIGRP 12, and here I have two options. You may not have these two available depending on your iOS version. You have the old format of configuring the summary where we actually need to specify the network and the mask, or I can use the shorthand notation network/ prefix length. Now I'm going to use, in this case, I'm going to use the traditional way of configuring it. I will use the other example on R2 in just a minute. So here I'm going to say that I want to advertise 192.168.64.0, and I want this to be advertised with /24 mask. When you configure your summary, or when you remove it, or when you change it, the routers need to resync, and I can see this log message here that indicates that there was an EIGRP resynchronization. Because the reason for this is that summarization is potentially going to change a large number of routes. And when you configure it, the router doesn't really know how much information needs to change. So it just initiates a resync process, which simply means resend all the routes that we have. Now, on R2, let's take a look at how our routing table looks. So remember, we had 2 external routes. And now, when I run the exact same command that I ran before, I'm going to see that I have a single /24 route, but take a note of this. This is no longer EIGRP external route. When we create a summary, even though we are summarizing external routing information, we are going to be summarizing this information, and the summary itself is going to become an internal EIGRP route. So now we have this one route in the routing table on R2, but a very significant change has happened in the routing table on R1. If I do show IP route EIGRP on R1, now what I'm going to see is that a new route has been added and installed in the routing table. I'm going to see now that for the summary that I just created, I have a route. So there is my /24, which is a summary, and I can see that it is pointing to null 0 interface. This is my discard route. I will explain what the discard routes do in just a minute, but I want to show you one more thing. So now on R1, I'm going to say show IP route 192.168.64.0, and I want to show you this piece of information. This route, this discard route that was installed on R1 in the routing table, was installed with the administrative distance of 5. And those of you with your fresh CCNAs, you know that distance 5 is associated with EIGRP summaries. But this is not going to be the administrative distance that is going to be assigned on the router that receives the summary. We can see that on R2, the administrative distance for the summary when it was received was 90 by default, which is EIGRP internal route. But on R1, on the router that actually created the summary, this route was installed in the routing table with the null 0 as the interface here. This is what got the admin distance of 5. So this is an important thing to note. Let's now take a look at the routes that go in a different direction. So from R2, we are advertising certain number of routes to R1, and I can see here that I do have 4 external routes that are being advertised, and I can see that they are all subnets of 192.168.100.0. So I can summarize these 4 as a single /24. So let's go ahead and take a look at what we need to do on R2 to perform this summarization. Now, you may remember that I mentioned that router 2 is configured to run or is configured for EIGRP with the named configuration mode. And when we have the named configuration mode, the right place to configure the summarization would actually be in the process itself. So I'm going to go into my router EIGRP Cisco here. I'm going to go into the address family, IPv4 Autonomous System 12, and here I'm going to go into the AF interface gigabit 1. So now I'm configuring EIGRP parameters that relate to this interface gigabit 1. And here I'm going to say summary address 192.168.100.0, and here I'm going to use the prefix notation. So now I have configured the summary address, and if I take a look at what actually ended up in my running configuration here, I will see that even though I have entered this using the prefix notation, what ends up in the running configuration is the old way with the network and the mask. So the prefix notation allowed me to just type a little bit less, but what ends up in a running configuration is the old stuff, so to speak. Now, if I go back to R1 and if I do show IP route EIGRP, I'm going to see the desired result. I can see here that I have 192.168.100/24, and I can see that it's facing on gigabit interface 1, and I can see here that it is an internal route. So the exact same behavior that I had in the other direction. And if I do show IP route EIGRP here on my R2, I will also see that I do have a null route here for the newly created summary. So the exact same behavior as I had before. Now I want to show you something different. I'm again on my R2, and if I do show IP route EIGRP, now if I take a look at the subnets of 192.168.200/24, I will see that this is a variably subnetted network. So now this is a little bit more helpful than that other output that we were dealing before, because in this output here, I'm actually going to see for all the subnets, I'm going to see the actual masks that are associated with these routes. But let's take a look at this network here, and let's go to our R1 and let's summarize this as a single /24. But before I do that, I want you to carefully take a look at this part of the routing table. Especially take note of this last route that we have here. So we have 192.168.200.248/30. The network, or I should say, this subnet does not cover, for example, .254 address. So there is no route for our .254 address. We don't have it. But when we create /24 summary, that summary will include this IP address here. So let's go now to R1 and create the summary. So I'm going to go to interface gigabit 1, and I'm going to say IP summary address EIGRP 12 192.168.200/24. Again, I have used this new notation, and if I take a look at the interface gigabit 1, I will see that what actually ended up in the running configuration is the old configuration format. So now if I do show IP route EIGRP here, I will see that my /24 is now in the routing table. So there it is. Now, remember that .254 network that I mentioned. What is going to happen now if I, for example, did a trace route to that IP address? So I'm now on R2. I do have the route for this IP address, so 192.168.200.254. I'm going to do the trace route and take a look what happens. What happens here is that we do send the traffic to R1, and then R1 tells us that this host is not reachable. This is the discard route in action. This is what discard route actually does. So here I'm going to talk now about discard route loop prevention. So what is happening here now at this point is we have R1 and we have R2. Now R1 has some more specific routes for 192.168.200x/y, but we do not have the route to .254. So this IP address doesn't have a more specific route. However, when we have advertised our 192.168.200.0/24 to R2, R2 suddenly has the route how to reach this IP address, and it can, as the result of that, send traffic to R1. Now, when this traffic arrives to R1, R1 is going to look, do I have the route how to reach this network? As it turns out, it actually does have a route, because when it generated this summary, it created this null zero route. So this traffic here that arrives, that goes to this address that doesn't have any more specific destinations, is actually going to be sent down this, what Cisco or what is in networking industry called bit bucket, basically a discard interface. And when it discards this traffic, it's going to send ICMP unreachable to R2. In other words, it did help prevent a certain kind of loop. What kind of loop? Now imagine that R1, on top of everything it has, had, for example, a statically configured default route pointing to R2. Let's configure that. So I'm going to go to R1 and I'm going to say IP route default to 10.0.0.2. So now if I do show IP route, I see that I do have a default route here in place on R1. And if I do the trace route from R2 to R1, I get the exact same behavior. But what would happen if, for whatever reason, I didn't want to have that discard route? First of all, is it doable? Can I get rid of the discard route? And second, what effect would that have on my network? Let's take a look. And as you might have guessed, yes, it is entirely possible to get rid of the discard route. I'm not going to go into analysis why would you want to do that, but it's important to know how to do it, because the same method that you would use to get rid of the discard route would be the method to change the admin distance of the route that gets installed as the discard route. By default, it has admin distance of 5, which is pretty much, after connected and static routes, the best admin distance you can have. But you might be in a networking scenario where you need a different administrative distance for this discard route, for this summary that you created. So when you want to get rid of the discard route, or when you want to change the administrative distance, it doesn't change. It's the same exact configuration that you have to do. It's just going to be the value that differs. But the important thing is to determine what kind of iOS you are running, because there is an old way to do it and there is a new way to do it. Prior to iOS 15, so this is the old way, the way to change the admin distance of the discard route or to disable it was to go under the interface where you have actually configured your summary address, create the summary, and then specify the admin distance at the end of the summary. So this is for versions of iOS up to 12.4, and this is for iOS 15.0 and above. So this is for versions up to 12.4. And this is how you would do it. If you specify the admin distance of 255, which is untrusted admin distance, this is going to result in not having the discard route installed. If you are running iOS 15 and above, again, it matters, are you running your EIGRP? Have you configured it using the numbered configuration mode or the named configuration mode? So let's take a look at the example of the numbered configuration mode. Again, this time you would go into router EIGRP and you would use the command called summary metric. You would specify which is the summary that you want to modify, and you would say which distance you want to use. If you use distance 255, that would create a summary route without installing the discard route. If you are using named configurations, the setup is fairly similar. You go into the EIGRP process, you go under the address family, but then you have to go into topology base. And this is Cisco's way of supporting multi-topology routing, and this is not something that you really need to concern yourself with. And just remember that the topology base is where you are configuring your main routing tables. So here, under this topology base, you would basically use the exact same command that you would use in a numbered mode. Summary metric, the prefix that you are modifying, what is the distance that you are configuring. And if you want to disable your discard route, you would use the distance of 255. So what effect will this have in our network? Well, now that we don't have this discard route, now that we don't have this null zero route in place, when R2 sends this packet to R1, R1 is going to examine its routing table. Where do I send this traffic? Do I have a more specific route? R1 does not have a more specific route, and the only route that it can follow is actually the default route. So what it's going to do, it's going to send the packet to R2. Now, R2 is going to look at its own routing table. Oh, I have the traffic that's supposed to go to 192, 168, 200, 254. Let me send this to R1. And then what we are going to end up having here is the loop. And this is the exact situation that the discard route is designed to prevent. one more thing that I would like to show you. Let's take a look at R2. If I take a look at the routing table on R2, I can see that for this network 192.168.64.0/24, I do have a route. I do have a prefix there. But on R1, if I do show IP route, I can see that for this 64 network here, I actually have 3 prefixes here. Well, actually, I do have 2 prefixes, and this is one summary, so I don't care about this one. What if I wanted to, for example, advertise my summary /24, and for example, in addition to the summary, I wanted to allow this one prefix to go through. The summary by default will, so to speak, suppress all the more specific routes. But what if I wanted to let some routes leak through? That's the hint. If I take a look at my interface gigabit 1, and if I go to the configuration where I defined this summary here, and if I use the question mark, I will see here that I do have an option to specify something called the leak map. Leak map is going to reference a route map, and every single prefix that is permitted by that route map will be allowed to be advertised in addition to the summary that would otherwise suppress this prefix. So let's create our prefix list to allow one of those more specific routes to go through. So let's allow, for example, this route to go through. So I'm going to say IP prefix list, let's call it PL1, permit this, and I'm going to say route map 1, permit 10, and I'm going to say match IP address prefix list PL1. So I'm now going to permit that one prefix explicitly to go through in addition to the summary. So I'm going to go to gigabit interface 01, and where I defined this summary, I'm going to specify the leak map route map 1. Now, when my neighbors resynchronize, if I go back to R2, if I do show IP route EIGRP, what I'm going to see now, in addition to my summary that I have, I will see that my 192.168.64.128/25 was actually allowed to go through. Let's now talk about EIGRP route filtering. With EIGRP, filtering is a really flexible thing. We can filter using access lists, prefix lists, route maps, the hop count, anywhere we like in our network. But generally speaking, there are 3 approaches to filtering in EIGRP. One is to use infrastructure that is provided using the distribute list command. Distribute lists can in turn reference access lists or prefix lists or route maps, and what we can do is we can specify these distribute lists either in the inbound or the outbound direction. We can specify them on a particular interface, again inbound or outbound, and we can even filter routes on a per neighbor basis. Say that on one interface we have multiple neighbors, we can say I'm going to allow only these routes, but only if they are learned from that particular neighbor. And this can be done again using access lists or prefix lists or using the route maps. And this can be done anywhere in the network on any of the interfaces. You can do this. However, you are not going to be configuring any interfaces for this filtering because all this is done in the router configuration mode. Another place where route filtering is relatively common are redistribution scenarios. When we are injecting external routes from some other routing process into EIGRP or any other protocol, we can specify route maps, and then in those route maps we can allow certain routes to go into the protocol or not go into the protocol. But I'm going to talk about the redistribution filtering when I actually talk about the redistribution later on. And the third method, which is relatively crude method in EIGRP, is to use the hop count for filtering. You might remember that hop count is one of the attributes, one of the components of the vector metric that is carried on all the EIGRP updates, and this can be used for crude filtering, that we can configure the router to say accept only the routes that have hop count of a certain number or below. And that can be done using router EIGRP and then specifying the maximum hops and then simply the number. But let's take a look at a few other examples of filtering. Let's say that we wanted to configure our network to allow only routes inbound, that only one route, which is 192.168.100/24. Now, this can be done, for example, by specifying the prefix list that is going to permit this one particular route. And then in EIGRP process, we are going to say distribute list prefix PL1 in. Now, keep in mind that if you use the distribute list, if you just specify the name here, you are actually going to be specifying the access list. If you want to use the prefix list, you have to use the keyword prefix, followed by the name, followed by direction, and optionally, you can use the interface here. So we could specify, for example, an interface to filter. So let's take a look at that example. So again, expanding a little bit on this example we had here, let's configure our filtering to allow only 192.168.100/24 if it was learned from 10.0.0.2 neighbor, which we know, for example, is on gigabit interface 1. So what we're going to do here is we are going to define two prefix lists. Prefix list 1 that is going to define our prefix, and prefix list 2 that is going to define our neighbor here. So this one here defines the neighbor, and this one here defines which prefix we want to use. And then in the EIGRP configuration here, we're going to say distribute list prefix PL1 gateway. So this gateway keyword tells us that what follows here is a prefix list that is going to define from which neighbor. So this is the keyword here that tells us basically which neighbor or neighbors we could have, for example, range of addresses here specified in our prefix list. So gateway PL2 in the inbound direction on, for example, gigabit interface 1. So with this configuration here, what we are doing is we are saying allow only this prefix learned from this neighbor if it was learned, that means inbound filtering, from gigabit interface 1. Now keep in mind that in both of these examples I have used the inbound direction, but you can easily use outbound filtering as well. These are just a few examples that I have. Now let's take a look at the example of filtering using access lists. Let's say that we wanted to use the access list to allow 192.168.100. Now keep one thing in mind. There is an absence of /24 here, because with access lists, when you are using them with distribute lists in EIGRP, unfortunately, there is no way to match the mask. The only thing that you can match is the route here. I'll explain that. So here I have the access list 1 permit host 192.168.100. Why host when I want to allow a network? Now, this is very important to understand, because in this context, this access list number 1 is not a traffic filter. It's a route filter. And the route that we need to match is 192.168.100, which means that this host 192.168.100 is the equivalent of me saying 192.168.100 followed by the wildcard mask of 0000, which means that this octet here needs to match exactly, this octet here needs to match exactly, this octet here needs to match exactly, and this octet here needs to match exactly. So this host keyword basically means that I'm using the wildcard mask of all zeros. So with this configuration here, I'm saying that this route needs to match exactly. Now, if you are asked to use the access lists to filter your routes, don't fall for a very common trap. Let me show you. one thing that is very, very common problem that people have when they're asked to use access lists for filtering. So let's say that we had our 192.168.100 network that we wanted to filter. And very often I've seen students write the access list that says, for example, access list 1 permit 192.168.0.0, and because we said that we want to filter /24, they usually write something like this. Now, this would be a perfectly fine traffic filter for the traffic coming from hosts from this network. But when used as a route filter, what we are saying with this configuration is that this octet needs to match exactly, this octet needs to match exactly, this octet here needs to match exactly, but for this octet here, we don't care what we have, which means that if you had in your routing table route 192.168.100, say 128/25, this access list as written like this would actually permit this to be advertised. So when you're using access lists as route filters, be on the lookout for this. What you want to do is you want to use this host keyword to match the routes exactly. Unfortunately, with access lists, you cannot match /24. So this could come as /16, it could come at /23, /22, /20, whatever it comes in as, there is nothing you can do about that using access lists. Now, that I have explained this, we are going to go into router EIGRP 12, distribute list, specify the access list number in. If this was a name, if you use the named access list, it will be the exact same syntax. Please note that there is an absence of that prefix keyword that is here if you are using this with prefix lists. Now, what if we wanted to use the access list to allow a certain network from a particular host or from a particular neighbor? Now, mind you, this is also very easily done using access list, but this time around we have to use the extended access list. The source part of the extended access list here is going to be used to match the gateway. And remember, that's EIGRP's name for the router. And the destination part will be used to match against the network. With same limitations, we cannot match the mask. Same rules apply as before. So now that we have used the extended access list, we are going to do the same thing. And again, let's say that this was on gigabit interface 1. So we can say distribute list 100 in, so in the inbound direction on gigabit interface 1. So we are applying this distribute list only for routes on gigabit 1. Other interfaces will not be affected by this filtering. Now, what if we wanted to use the route map to allow 192.168.100 on gigabit 1? We are going to define prefix list or access list, but prefix lists are more flexible for this purpose because we can actually match the mask with them. So we're going to define the prefix list, we're going to define the route map, we're going to say match IP address prefix list, PL1. Don't forget that in the route map, if you don't say the prefix list here, the name that you type is going to be referencing the access list, and this is not what you want if you want to use the prefix list. And then in router EIGRP process, we would say distribute list, route map. The same way we would have used prefix list, this time we are saying we want to use the route map 1, in the inbound direction on gigabit interface 1.